Hello folks, it's time again, time for another super boring video. Today's topic, given the old Halloween stuff going on at the minute, will be our ZombieVerter VCU. So this is the much heralded part 2 of our kind of a user manual series and updates on the VCU project. Serious health warning, this is a boring video. It's very long, it's very uninteresting. There are no dancing girls, there are no explosions, there is nothing interesting or redeeming about this video at all. So, if you found yourself here by accident, immediately hit the stop button, go up there, type funny cat video and press enter. You will be safe then. Additionally, just another little health warning, our friends at PooTube will be putting adverts in my videos. If you would like to watch my videos without adverts, pop over to Vimeo, where you can see the same super boring content free of those pesky distracting adverts that actually would be probably more interesting than the video. So I'll leave that up to you. Anyway, here we go, delving into our ZombieVerter VCU. Hello folks, and welcome to what is going to be the first of 2 parts that we're going to do for you on a kind of an instruction manual and an overview of our ZombieVerter VCU. So, first thing that I'd recommend anyone to do if they're new to this is firstly visit this link here, which I will put in the video description for you. This is the wiki page on the Open Inverter website, and it gives a very good basic description of what we're trying to do here with this particular item. Now, further on from that, there is a video here, which I will also link in the description, of the basics of what the thing does and how to build up the kit. Now, this kit build video here is a little bit dated because the semiconductor shortage is really causing it to be a kind of a movable feast in what components I have to include with the kit that the end user has to fit, and what components will be on the actual board itself. So once you get through all this, first thing that you're going to see here about midway down the page is the pinout diagram, and we're going to focus on this here firstly in order to get a familiarity with what all of these pin names do. The pin header is 56 pins, and up on the top part here you will see that there is a number on each pin. That number corresponds to a number that you will see on the pin header itself. So each of these wires here corresponds to the number that you will see on this diagram. So we're going to start at the bottom right and work our way from right to left all the way back up here. So down here is our first 2 which are quite basic, which is our ground. So we connect this to our vehicle 12 volt ground, and our permanent plus 12 volt supply. So this needs to be connected to our vehicle's 12 volt system permanently via a small automotive fuse. So a few amps, 2 or 3 amps would be more than sufficient for that. So this is ground and permanent 12 volts. Now the next 2 here, reverse direction and forward direction. Now, depending on what type of a conversion that you are undertaking, you may or may not need either or both of these signals. If you are using a vehicle that has CAN-based gear shifter and things like that, such as the BMW E65, then you will not need these. Most people will, and will need at least one. You will need at least one if you are using a gearbox that has a mechanical reverse, so you never need to reverse the motor. If on the other hand you are using a vehicle that, let's say, has a transaxle, like say a Toyota Prius transaxle in there, or a Nissan Leaf transaxle, say, and you will want to be able to change the direction of the motor. So these two signals here need to be applied. So obviously we apply a signal to the forward direction, the motor will run forwards, and when we apply a signal to the reverse, the motor will run in reverse. So what kind of a signal? Well, it's really simple. We just give them 12 volts to turn them on, or disconnect them to turn them off. So for example here, if we apply 12 volts to the forward direction pin, we will ask the VCU when it is ready to go to rotate the motor in the forward direction. Likewise, if we apply a signal to the reverse direction pin, when enabled, the VCU will request negative torque to run the motor backwards. Keep in mind that these directions are, what's the best word for it? They are relative to whatever drivetrain and vehicle that you're building, and there is a capability within the web interface to flip these, and I will show you that when we get to that section. Next up, start. So the start signal is designed to be used with the traditional kind of an ignition switch, where we rotate the key against a spring into a start position that would have traditionally engaged the starter motor on an internal combustion engine. So in this case, start is a momentary 12 volt signal that will request the VCU to start up, so to initiate pre-charge and to start waking up various components. HV request is another 12 volt on off, so I guess a digital signal. It is in this case designed for use with chargers that may have a simple digital means of requesting that the high voltage be applied. So if we apply 12 volts to this pin and we have the necessary mode set in the web interface, this will request the charger or the VCU to pre-charge and to bring up the high voltage system, but not to bring up any of the drivetrain components. Next up, we have GP 12 volts input. That is a general purpose 12 volts input. It works in the same manner as the ones that we've just described, and is reserved basically for future use. Brake input is fairly self-explanatory, but just to be super clear, this is another digital 12 volts input. Typically this would be connected to a brake light switch, so that when the brake pedal is applied, we apply 12 volts to this pin, and when the brake pedal is released, we take that signal away. This is used by the VCU for such things as regen, safety interlock between the brake and the throttle. So If the VCU sees the brake and the throttle applied at the same time, the brake will take precedence always. Speaking of throttle, the next 4 pins here. So we have plus 5 volts throttle, throttle 1, throttle 2 and throttle ground. So this is a 5 volt supply for a Hall effect throttle pedal. We have our 2 analog channels, so throttle 1 and throttle 2, and then our ground pin for connecting our Hall effect throttle pedal. I will show you when we're working with the test system in the workshop, just basically how that works. Now the VCU has got 3 CAN bus interfaces, and we're going to talk about those next. So we have CAN external high, CAN external low, and then when we come back over here we have CAN external 2 high, 2 low, 3 high and 3 low. So CAN external high and CAN external low are designed to connect to a vehicle's body CAN or powertrain CAN or general CAN. There's all kinds of different names for them, depending on what vehicle that you're looking at and whom is writing the documentation. But what this is designed to do is to mimic the fossil fuel drivetrain signals from a range of vehicles. So we have a few BMW vehicles, Volkswagen vehicles, and fairly soon we'll have some Toyota vehicles. The plan is to have a menu here that we can just choose whichever vehicle that we want, and the VCU will then mimic all of these CAN signals, so as that the rest of the vehicle will continue to work as if it was still possessed of its original fossil fuel drivetrain. So the aim of the game here is that folks won't have to worry about any of the CAN hacking and all of, trying to work out what does what. You literally just connect 2 wires and forget about it. CAN external 2 low and CAN external 2 high are designed for connection to the CAN system of an OEM drivetrain, so for example a Nissan Leaf drivetrain, and the ISA shunt. And I will be showing you soon what the ISA shunt is. I'll explain why we need it. And I will then show you on the test setup where CAN external 2 connects to a Nissan Leaf drivetrain that we use for testing. Finally, CAN external 3 low and CAN external 3 high. They have a variety of functions. One of them, we're currently working on at the time of making this video, is for CHAdeMO fast charging CAN. Another function that they have is for controlling the Chevy Volt stroke Opel Ampera cabin heater. It's one of the 2 functions that we have at the minute for CAN 3. CAN 3, unlike CAN 1 and CAN 2, has got several different transceivers connected to it that can be chosen by a variety of solderable jumpers. It can do standard high-speed CAN, it can do single wire CAN, and it can do fault-tolerant CAN. So there's 3 different types of CAN transceiver that can be connected to the CAN 3 system. Next up, we have LIN, which I believe stands for Local Interconnect Network. This is a single wire bus that is used in modern automobiles for purposes of communicating with low priority items. One of the things that is currently being worked on for is control of a Volkswagen 6.5 kilowatt cabin heater. There'll be various things like, it's kind of hard for me to think about what other things are on LIN, but I guess the cabin heaters and other kind of things that wouldn't be exactly safety, you know, they wouldn't be super necessary, that you could still safely drive the car if you didn't have them. So that has a LIN transceiver in there, and we can communicate with LIN components, I guess is the short description. Now, these next signals here, HTM plus and minus, MTH plus and minus, CLK plus and minus, and REQ plus and minus. These are all part of the same family. And what they are designed for is connecting to a variety of Toyota hybrid inverters. So for example, Lexus GS450H inverter would connect using this bunch of signals here. Toyota Prius Gen 3 and probably a few future ones when we get around to them, like other Lexus and Toyota systems. This is what is called a synchronous serial communication system, and it is implemented in both hardware and software on our VCU. Probably the most I guess well-known example of the use of this would be on the Lexus GS450H drivetrain that I installed in the BMW E65. So lastly on this block here, we have ignition T15 in. So ignition T15 in is closely related to our start signal. So whereas our start signal should be applied momentarily when the key of a traditional ignition switch would be rotated against the spring to engage the starter, ignition T15 in is another digital 12 volt input that should be switched on when the key is rotated to the on position. In the Bosch terminal, I guess whatever they call it, labeling system, T15 is terminal 15, and terminal 15 in a vehicle is basically given 12 volts when the key is in the on or the run position. And this is used by the VCU to determine when the driver would like the VCU to go into a run mode and to come back out of. So when we disconnect 12 volts from ignition T15 in, the VCU will shut down our 12 volt, or will shut down our high voltage system and our drivetrain. Now, up to the next block of signals. So we have trans PB1, trans PB2, trans PB3, trans SL1 minus, trans SL2 minus, and trans SP. So this block of signals here are related to our HTM and our clocks here for our Toyota hybrid systems. These are designed to control the valve blocks in particularly the Lexus GS450H transmission for purposes of shifting gears and monitoring it and things like that. Moving to the left, we have pot 1 and pot 2. Those references are shorthand for potentiometer 1 and potentiometer 2. Our VCU has got 2 digital potentiometers in there, and their outputs are brought from these two pins. They are ranging from 0 to 5 kilo ohms or 5,000 ohms, and they're designed to mimic the fuel gauge sender in a traditional liquid fuel tank. So you've typically got a little level float in there that goes up and down depending on the fuel level in the tank, and that drives a fuel gauge, so a basic analog fuel gauge. And pot 1 and pot 2 are designed to mimic that and basically drive a fuel gauge depending on the state of charge of your high voltage battery. They can of course be programmed to provide any other mimicking of resistances that may be required in the future. We then come to these three signals here: inverter power LS switch, main contactor LS switch, and pre-charge LS switch. So first of all, the LS is shorthand for low side. Low side means in this case that we are switching the ground of the device that we wish to control. Now, if you don't understand what that means, I'd suggest having a look around the web and or YouTube, and there's some very good descriptions of the difference between high side and low side switching of relays and other loads in an automotive setting. The inverter power low side switch is designed to switch a relay coil that then controls the 12 volt feed to an inverter, such as a Nissan Leaf inverter, a Lexus inverter, a Prius inverter, it's the other one I've been messing about with, the Mitsubishi Outlander inverter. So this signal here allows the VCU to control the 12 volt supply to an inverter, powertrain, and various components like that. Main contactor low side switch is designed to switch on and off the main contactor in our high voltage system. Likewise, pre-charge low side switch switches on and off the pre-charge contactor from our high voltage system. And if you don't understand the function or the names of these, I would strongly suggest do a little bit of research first before proceeding any further. Now we have GP out 1 here, which in this case I will have to update the diagram a little bit, because GP out is shorthand for general purpose output. This is a low side switch, and in this case it has been used within the VCU for the negative side contactor. So our main contactor low side switch would typically switch our positive side main contactor, and our GP out 1 will switch our negative side main contactor. So we have a few more signals here: oil pump PWM, MG1 temp plus and MG1 temp minus, MG2 temp plus and MG2 temp minus. Well, guess what? These signals are again designed, these 5, so oil pump PWM, MG1 temps and MG2 temps, are designed for our Lexus and Toyota hybrid systems. In this case, this oil pump PWM is short for pulse width modulation, and that will provide a speed control function for the external oil pump as used on some Lexus hybrid transmissions. The temp is short for temperature. We have 2 temperature sensor inputs that we can take temperatures from motor generator 1 and motor generator 2 in our Lexus and Toyota hybrid systems. As you will see here, there's actually quite a bit of dedication within the pinout to the Lexus and the Toyota systems. And that's one of the unique features of this VCU. So, working away here across the top, we have DAC 1 and DAC 2. That stands for Digital to Analog Converter 1 and 2. So these are two signals that originate from the STM32 microcontroller in our VCU. And they are amplified and can provide an analog signal on these pins of a wide variety of shapes and sizes. They're not implemented as the time of making this video, but they are in there for future proofing. So if I don't know, I guess we could drive instruments with them, we could control various functions within a vehicle or a drivetrain that may need us to mimic analog voltages. So that's what these guys do. Analog 1 in and analog 2 in are fairly self-explanatory. These are analog signals that can be taken in by the VCU and interpreted by the microcontroller to perform a variety of functions. They are allowed to span between 0 and 5 volts DC and are currently, again, not implemented, but are there for future expansion. Next up, we have PWM1, PWM2, and PWM3, short for pulse width modulation. These are 0 to 12 volt signals amplified by some analog circuitry on the VCU, and are driven by the STM32, and again are not implemented at the time of making this video, but will be here for future expansion to drive things that may need PWM signaling. An example of which might be to speed control a fan, or to control a basic heater or stuff like that. GP out 2 and GP out 3 are similar to all of our other 12 volt switches. These are low side protected drivers and can be used for a variety of functions, like switching on and off a coolant pump, or providing other switched services that may be needed. Finally, over here on the top left, we have RS232TX and RS232RX. In this case, RX and TX are respectively short for receive and transmit. Within our VCU, we have a Wi-Fi module for connecting to the VCU and changing settings and updating firmwares and things like that. It may be desirable to not have the Wi-Fi module within the casing of the VCU, or to have some other mechanism of communicating with the system. Thus, there are some solder jumpers on here that enable the VCU to transmit and receive RS232 information at 115,200 baud to some external device that may provide connectivity of one form or another. They're provided mainly for future expansion, but the hardware is there. So, folks, at this stage, I'm sure you are completely bored out of your skulls. But that is a brief, as I can reasonably make it, description of the 56 pins of our VCU. Okay, so now that we've looked at our VCU, there's another very important component that we need to have, and that is the ISA shunt. So if we go back to our VCU wiki page here, which again will be linked in the description, you'll see there is a note here that says, in addition to the VCU, the inverter and transmission, you will require a specific CAN bus connected shunt. And there's a link to that. That pulls us up then to the wiki page for the ISA shunt. Now I call it the ISA shunt because my pronunciation of German, particularly umlauts, is terrible, and I'm not going to embarrass myself by trying again. So, strongly suggest reading the wiki page here. Also on this page you will be linked to the manufacturer's website, where you can get some more information on the part, including a full data sheet. So, what is it in brief, and why do we use it? Well, in short, the ISA shunt provides the battery and broken wire, provides the battery monitoring functions for our VCU. I'm going to make a fool of myself on camera, hopefully. Yes, brilliant. I love this, and you're going to guess that the only thing that I really hate about it are the fact that for a really rugged automotive part, they just had to use these silly little connectors. Anyway, what it does is it monitors current. So through these big bolt terminals, we pass our full current for our EV systems through here. It can monitor 3 voltages completely independently and fully isolated. It measures temperature, it measures amp hours, kilowatt hours, and a whole bunch of other things that are very useful for us to know. Now our shunt then transmits that back to our VCU by means of CAN bus. And if we refer back to our, where's my diagram gone here? Here we go. So if we refer back to our diagram, we'll see CAN external too low and CAN external too high, as well as being connected to the drivetrain components like inverter and charger and things like that, have to also be connected to our ISA shunt. So this kind of heavy duty metal part basically needs to form part of the negative battery feed. So we would typically put our battery negative on here, and then connect all of our load negatives, so charger, DC-DC converter, inverter, and all that, via their respective contactors back through our ISA shunt, so that it can measure the energy going in and coming out of our high voltage battery system. And it can monitor via these connectors here up to 3 voltages related to our high voltage battery. So to just give you a little demo here, we plug into this one with one of those silly little connectors here, and if we go over to our VCU here, we have on the bench, which is connected to this shunt. if we go down to spot values, you'll see that we have UDC, UDC2 and UDC3. Now they're currently all reading pretty much 0 volts at the minute. But if I take just a little 9 volt PP3 battery, and I'm just going to connect the positive just to this, and I'm going to touch the negative here. We'll see UDC comes up to 9.5 volts, which is our battery voltage here. And if we take it away, that voltage goes away. So that's just one of the features. And it clocks up things like current, power, kilowatt hours, amp hours, and from that we can derive things like state of charge for our VCU. So while it is possible to run the VCU without the ISA shunt, I really strongly recommend that you get yourself one of these. Now the next question that you're going to ask me, and it's a very frequent one, is where do I actually purchase this? So you cannot purchase these from me, okay? I do not sell them, but I will tell you where you can buy them from. And there is this website here. This is, I believe, based in the Netherlands. Very nice gentleman runs this website and web shop, and he sells the ISA shunt. So he sells it with a variety of options, like different currents, different configurations, and I believe he also sells it with the connector kit. So those silly little connectors. Folks will kind of look at this, and I know some people say, oh, it's really expensive, I don't want to spend this, you know, is there some way around it? Can I just make something? Can we use an Arduino? Folks, you can do any number of things, but what I'm trying to do with the likes of the VCU and the ISA shunt is to try to standardize this particular system here. So again, you know, feel free to take bits of it and do whatever you feel you can do depending on your skills and abilities. But what I'm trying to do is to make it not, you know, the whole just plug and go kind of thing, but to make it reasonably modular, so that we have our VCU, we have our shunt for monitoring our battery, we connect our CAN up to do various other functions. So VCU and shunt, this is it. This is where we're going to get it. I will see if we can put that link on the wiki page. I think that'd be a good idea, so that folks know where to go to actually purchase this guy. Okay, so now that we've looked through some of our connections and ISA shunt and stuff like that, it's time to come have a look at the web interface. Now, there's a good deal of overlap between how the VCU web interface works and how it works on the standard open inverter boards. But not all of the functions work as originally designed. So that's one of the things I just want to get straight out of the way here. And we're going to talk a little bit in this section about software updates, how they work, how they can sometimes go wrong, and how to get yourself out of them. But before we get into that, let's first of all have a look and see where the software is and where we can get it, and how we can, if we so wish, make modifications or indeed contributions to it. The ZombieVerter VCU is a fully open source project. It is licensed under GPL3. So what that basically means is that you can take this, do with it as you please under the terms of GPL3. I very much believe in open source hardware and software, particularly in relation to electric vehicles, because I think we need to start building up what I tend to call tribal knowledge about how they work, and more importantly, how to maintain them and fix them when they go wrong. And the little bit that I can do is making my designs available freely to others. Now, so GitHub page is here for the software and indeed the hardware. Little bit of a description here in the README in how to compile it, and some of the features and some video links. This will be constantly in a kind of a state of update and flux here. I'm not going to go through how to build the software here. That's a little bit too specialized. If you don't know how to do that, there's loads of ways to learn how to. It is basically the microcontroller here is an STM32F107 VCT6. So this is where you can get the software. There are several branches. The master is the one that at the time of making this video is running in 2 out of my 3 cars. Runs CCS fast charging and driven the guts of 10,000 miles between the 2 vehicles at the time of making this video. The inverter object refactor branch is where Johannes is cleaning up my dog's dinner of a software and is adding in some really neat new features for us here. So we've got some good people contributing to this. Broadly, when it comes to software, I do not know what I'm doing. I'm learning and making tons of stupid mistakes along the way. But the good news is I test all of this stuff in my own cars and in things like this here, so that at least the serious screw-ups won't make it into the GitHub. So here's where you get your software. Now, updating software for most things that we encounter means cables and computers and even some specialized software that needs to be installed on your computer to communicate with the stupid thing that you're trying to update and all of this. One of the really neat features that the open inverter system has, and that I have ripped off here, is the ability to perform software updates just over the Wi-Fi interface. So you don't need to have anything installed on your computer at all. We just use a web browser. So to perform a software update, you first of all need a bin file, which is short for a binary. As this project evolves, there will be more and more pre-compiled binaries available via the GitHub that will have additional features and bug fixes and things like this in them, so that you won't have to understand how to mess with all this stuff. All as you will need to do is this: click browse, select the bin file. It'll be called stm32vcu.bin. Double click it. then hit upload. You will get a progress bar and your LEDs in your VCU will do a dance. You should get update done. The processor will reset and voila, software update is done. Now, later in the video, or it might even make it into part 2, where I'm demonstrating running the VCU with the Nissan Leaf test system in the workshop, I will demonstrate to you what can go wrong with a software update, explain to you why that goes wrong, and explain to you how to get yourself out of it should it actually occur. One thing that I will mention at this stage is that even if we even if the software update goes wrong and the VCU appears to be, as they say, bricked, it's actually not, because the bootloader which is the program within the microcontroller that controls the startup of the main program and the execution of the software update, is not overwritten by a software update. So it is always in there, and we can get it to save us from any particular nightmares. So now that we've that bit out of the way, let us have a look at our web interface. And we can access that just by means of a IP address, just with a web browser. That's it. You can do this from any computer that has a network connection, be it this desktop here, be it a laptop, be it a phone, a tablet, hell, even a Kindle you can connect to this thing with. So you're not tied down to any particular software that needs a certain operating system, or needs this or needs that, or doesn't have this driver or this connection, or whatever it may be. So, starting at the top, commands, update, parameters, spot value, plot, and refresh. What do they do? Well, let's click on them. Click on commands. Commands brings us up these series of radio buttons here. Save parameters to flash, restore parameters from flash, start inverter in manual mode, stop inverter, display error memory, and reset CAN mapping. Now, these are directly brought over from the inverter system. And with the exception of start inverter in manual mode and the stop inverter button, these other two, so save parameters to flash, restore parameters from flash, display error memory, and reset CAN mapping, work as normal. Save parameters to flash does exactly what you might think. So when we change something, we want to press that button to save that to the permanent or non-volatile memory within our VCU. If we click restore parameters from flash, it will restore all of the parameters to their default value. If we click display error memory, it will show us the error, the last error that was stored within the VCU. And if we click reset CAN mapping, it will reset any custom CAN messages that we may have had saved off in our chart. Now, a lot of this will make more sense as we make our way down through the web page here. But let's again go back up here and click save parameters to flash. Now, nothing appears to happen. But what you need to do is scroll down a little bit and come down to messages. When we get to messages, we'll see that there is a message. It says CAN map stored, parameters stored, and CRC will be equal to some 32-bit hex number. If we hit clear, the messages go away, and if we went back up here again and hit save parameters to flash and came back down, we would have our message again. So when we hit this button here, we want to scroll down here and make sure that we get a message telling us that it has actually stored the parameters. If we hit display error memory, likewise, we want to come down here. We get a message and it will say no errors in this case because we've no errors. Again, we can clear. And if we say reset CAN mapping, we come down here and it will say all message definitions cleared. So again, this is once we execute a button here, we should get a corroborating message here under the messages area, which we can then clear by pressing that button. So the send custom command is again brought over from the inverter system and is not really used at the minute with the VCU. There are two more things that we can click on. One is Wi-Fi settings, so let's click on that. So what you will see here is we get the choice to do two things with our Wi-Fi module. We can get it to create its own access point by giving it a SSID and a passphrase, or we can get it to connect to a local network, which in my case is what I have here. I've connected the VCU to the house Wi-Fi here, and the router in my house has supplied it with this IP address, which is the IP address here that we're accessing our system from. So again, if we just reset that, it'll basically connect back to our system. The other thing that we can do is we can start a remote support session. We can click on that. And this basically then will allow mostly Johannes, because I don't know how to do it, to connect to your VCU and to provide remote access for diagnosing problems and fixing them. So we then come to our UART update, which is where we do our software updates from. And I'll do that again here just to familiarize people. So pick our stm32vcu.bin. We click upload. And there it is. The SWD update function at the minute does not work. So we then come down to parameters. And indeed, if we go back to our buttons up the top where we started, if we click commands, it brings us back here. If we click update, it brings us down to our software update. If we click on parameters, it brings us down to our parameters area. Now, before we get into the meat of the actual parameters themselves and what they actually do, let's have a look at a few of these areas here. If we open the parameter reference, it brings up this web page here, which describes what the parameters within the open inverter system do. Some of these have been brought over to the VCU, but obviously the ones that relate to motor and things like that do not. Download parameter file. Let's click on that. So all of a sudden, my web browser now is asking me to save a params.json, which is a JSON file, which is basically now going to grab all of the parameters that we have set, put them in a JSON format, and let them be saved somewhere for sharing or for reloading up or modification. So quite a useful feature. Next then there's a browse button. If we click that, it now wants a JSON file. And if I select one, I can hit the apply parameter file button, and this will then apply those parameters to all of their matching counterparts in the parameter database. We can submit these to the Open Inverter server. So if we have a really good set of parameters here that's working for us, we can choose to submit them. We can subscribe to them. So that's a little bit, the subscribe and the submit are probably more relating to the inverter rather than the VCU system here. So let's get down into the parameters. And parameters have a name, a value, a unit, a minimum, a maximum, and a default. So our first group of parameters is vehicle. And we can choose an inverter and we can choose a matching vehicle. So at the time of making this video, we have Leaf, Lexus GS 450, Open Inverter, and Prius Gen 3 modules that we can choose from a menu. So these are our drivetrains, and we can then choose which vehicle that we would like to use. So ultimately, the main goal is to have a big long list of drivetrains, a big long list of vehicles. When you get your VCU, you just connect up, choose what you want to do here, which corresponding drivetrain and vehicle that it is that you are using, and that's it. That's your configuration done beyond setting up whatever driver preferences that you may want to have. So throttle, which is kind of full of a lot of things now, needs to be kind of broken out a bit, but again, this is what we've got at the time. Pot min, pot max, pot 2 min, and pot 2 max. These are our analog throttle values, so the minimum and the maximum values for those parameters. I'll explain these a little bit better when we're working on the test system, because I'll physically be able to show you how to perform a throttle calibration. Regen Travel is how much of our throttle pedal do we want to allocate to regenerative braking. So this is for our, I guess they call it single pedal driving kind of thing. Regen Max is how much of the maximum available torque from our chosen drivetrain that we wish to allow the VCU to apply as a braking or a regen action. Pot mode, we can have a single throttle or a dual channel. Direction mode, this comes back to what we were describing with our reverse digital input and our forward digital input. These can be a switch, so we need to have the voltage applied for the direction mode to remain valid. It can be a button, so it can be just a push button to select, so a pulse will select forward and a pulse will select reverse. We can then have button reversed and switch reversed. So if you find in your particular vehicle that forward is reverse and reverse is forward, you can choose to flip them here within the web interface to correct that problem. Default forward is, again, that's more so from the inverter system, but if we select default forward, it basically means that the forward direction is always selected, whether we apply signals or not. So we'll just go for switch. Trot ramp is the percentage per 100 milliseconds of throttle that we want to ramp. So for example, if I have this in the default value, which is 100% in 10 milliseconds, what that means is if we slam the throttle pedal down to full, we will reach 100% torque request from the VCU in 10 milliseconds. So we can set that anything from 100 to 0.1 percent of throttle in 10 milliseconds. Throttle ramp RPM is where we want the throttle ramp to stop. So that's not really used at the minute here. Rev Limiter means just that. Where we basically perform a hard cut of our torque request. So if we, in this case here, if we exceed 6,000 RPM, we will command a zero torque request just to stop motors and drivetrains from spinning up to too high of a RPM. Breakout is the percentage of regen at which we want to turn the brake lights on. Now BMS lim high and BMS lim low are currently not implemented within the VCU firmware, but are left here for the purposes of future integration. UDC min is the minimum voltage at which we are going to allow the VCU to request torque. So this would be the minimum voltage that we want our battery pack to ever be at. So it's this is where we would set our kind of lowest cutoff. UDC max, likewise, is where we would set our maximum voltage that we would allow the VCU either to command regen torque if we're in drive mode, or to allow charging to cut off if our charger decided to keep charging. And UDC lim is basically where we would initiate a hard shutdown of all systems if the voltage ever exceeded that point. IDC max and IDC min let us set current limits for both driving torque and, for both driving current and regen current. So we can set these to more sane values, and they will prevent too much current being drawn or too much current being put back in to our battery pack. TMPHS max, TMPM max. TMPHS max is shorthand for temperature heatsink maximum. This is the maximum temperature at which we allow 100% driving and regen torque to be commanded. If the temperature exceeds that, we start to derate. Likewise, TMPM max is temperature motor maximum, and that has the same effect. Trot max and trot min are shorthand for throttle max and throttle minimum. So how much of our throttle do we want to allow? By default, these are 100%, but we might choose to limit these to a lower value, for example, for people that may not be familiar with driving our vehicle. Gearbox control is dedicated to the Lexus GS450H gearbox. So what gear that we would like to be in, be it low gear, high gear, or automatic. Automatic shifting is not implemented at this time. And oil pump is just a static value of oil pump speed that we would like to command. Cruise control currently is not implemented within the VCU firmware, but will be in the future, so we're keeping these parameters here. Contactor Control. This is where we set our voltage that we would like the pre-charge voltage to achieve before we command the main contactor to close. Cruise light and error lights currently not implemented. They're just brought over from the inverter. Likewise, can speed and can period, again, are not used. These are just brought over from the inverter. Charger control is where we can set up things for our battery charging. So charge modes, we have off, HV on, just is basically a manual way of requesting the VCU to initiate a HV startup. External CAN allows us to command the charger via CAN and to receive from the charger via CAN. External digital allows us to do the same, but just with the 12 volt signal, such as HV request that we saw earlier. And the volt ampere option is going to be implemented soon, hopefully, for controlling a Chevy Volt Opel Ampere charger directly. Battery capacity, that's where we put our battery capacity in kilowatt hours. This is just basically used for calculating of SOC. The charger interface, currently we can have unused i3Lim, CHAdeMO or Leaf PDM. So i3Lim is the BMW i3 charging interface module, which I use in the E46 Touring. And that lets us use things like CCS fast charging and other fun stuff. CHAdeMO, self-explanatory. That'll use CAN3 for CHAdeMO fast charging. And Leaf PDM is the Leaf, I think it's called Power Distribution Module. So this lets us use the AC charger and the DC-DC converter, and hopefully before too long the CHAdeMO fast charging functions of the Leaf PDM. Voltage set point is the CC CV set point that we would like our system to hit. The power set point is the maximum power that we would like our charger to run at. IDC term is the DC current for termination. So typically what we will do, we will hit a voltage set point, wait for the current to come back down, and then once it goes under the IDC termination value, we will terminate charging. CCS I command is used for manually commanding CCS or indeed other fast charge currents. At the minute, it's a holdover from when I was debugging CCS. It's not used. CCS iLim is we can put a value manually in here for what we would like our maximum CCS or indeed CHAdeMO current to be, and depending on the current that is the current there, depending upon the maximum current that's available from the fast charger, we will either use the lower of those two values. So for example, if our fast charger provide 125 amps and we say 100 amps here, it will use 100 amps as the maximum. CCS SOC limit is pretty self-explanatory. It's where we will terminate charging based on state of charge. And charger control basically lets us go enable, so we can charge all the time. Disable, where we don't charge, or timer, where we can schedule charging to occur. Heater module. So we have, at the minute, we have none, Ampera and Volkswagen heaters. At the minute, it's just the Ampera heater that's implemented, but the Volkswagen Lin-based one will be implemented soon. And our control can be disable, enable, or timer based. And in here then we can set the maximum heater power that we would like. RTC, or real-time clock module. This allows us to set the day, hour, minute, and seconds of a current time. Then we can set the charging time, charging minutes, and charging duration. So charging hours and charging minutes are the time at which we would like charging to commence. And the charging duration in minutes is a form of a safety timer where we would like the charging to terminate after a specific time if it has not already done so by means of our DC termination current set point here. Preheating will be the very same thing, which will allow us to preheat our vehicle to be warmed up and demisted, etc., using our heater system that's currently not implemented. Spot values, I'll run quickly through here because it's pretty straightforward. I'll focus on a few and I'll mostly just run through them. Version is just a software version, hardware is the hardware version. Op mode, critical one. This tells us what mode our VCU is currently in. At the minute we are in off. So if I were to turn my terminal 15 on and press my start button and then refresh my web page, we are now in run mode. If I turn my terminal 15 off, refresh, we go back to being in off mode. Other modes that we can have depend upon what our system may be. A most common one will be pre-charge. So if I disconnect my system here, and if I turn my terminal 50, if I disconnect my high voltage, turn on, we will go into pre-charge and we will eventually time out after 5 seconds. So if I refresh again, we just go back to off mode and we get our last error pre-charge here. And our status is UDC, or the high voltage DC, is below UDC switching set point. So we are below that. So basically if we have a break in our high voltage system, we will get this particular error. So if I reconnect my ISA shunt, just hit refresh, we see our UDC comes back up. And if I press my start button again, that's our key to the start position. If we refresh, we're indeed back in run mode and we have status none. So, switch off one more time and we're in off mode. One other mode that we can get is charging mode. So, be it commanded via CAN or via a switch. In my case here, we can go into, if I'm not doing something stupid, which I am, oh, I am doing something stupid. See, I've done something stupid. So, why didn't we go into charge mode here? Well, because if we go back up here, charge modes, we want to have in external digital so that we can use a switch. So if we do that, if I now flick my switch on, I click refresh, we are in charge mode. So, switch back off, off. UDC is our number 1 voltage measurement from our ISA shunt. 2 and 3 are measured on the other connections on our ISA shunt. Delta V is the difference between these. Inverter UDC is the voltage measured by whatever inverter that we have connected, typically transmitted via CAN or synchronous serial. Power is our power in kilowatts. IDC is our DC current. Kilowatt hours, amp hours are our current consumed or returned kilowatt hours and amp hours. SOC is calculated from the battery capacity that we provide earlier and the kilowatt hours value received from our ISA shunt. Speed is the current motor speed in RPM. Vehicle speed, self-explanatory in kilometers per hour. Torque. This is the torque command that we are currently sending to our connected inverter. Pot and pot 2 are the analog values being read from our throttle pedals. So our throttle pedal, the two analog channels, and I will describe those in greater detail on our testing system. Likewise, pot brake and brake pressure are measured from our vehicle, are transmitted from our vehicle, host vehicle. Pot nom is the percentage of throttle that we are currently commanding, and that will relate to torque. So whatever mapping, that is what that applies to the respective inverter module. This will be translated into a value of torque that is then transmitted either by a CAN or synchronous serial or whatever other system. Direction is currently neutral. If I enable the direction and refresh my web page. Oh no, because I don't have that connected. See, genius. So I don't have any direction currently enabled here because I don't need it for what I'm doing. Inverter just tells us, just confirms the selected inverter, which is Leaf Gen 1, and vehicle is Volkswagen. Our charger mode is indeed set to external digital. So these three here are just used to confirm some of the selections that we have made earlier. Temperature heatsink of our inverter, temperature motor. Temperature auxiliary is the current temperature taken by the ISA shunt, which is reading a nice warm 23 degrees centigrade. UAux is our 12 volt system voltage as measured by the VCU, and that's currently wrong, so I need to fix that. Going to skip down here a little bit. These ones don't do anything at the minute. But these are our digital inputs for cruise, start, brake, forward, reverse, and BMS. Of these, start, brake, forward, and reverse are the ones that are implemented. So they're currently off. When they're switched on, these will change to being on. Likewise here, handbrake is transmitted by the host vehicle. Gear 1, 2, and 3 come from our Lexus and Toyota hybrid systems. T15 stat is an important one. It's currently off. If I turn my terminal 15 on and refresh, T15 goes on. So that means that we have the key in the on position. If we turn our key off and refresh, we go to off. Inverter status is the inverter on or off. In this case, it's off. Gear feedback is from our Lexus Toyota system, so whatever gear that we're currently in, as measured within the valve block. Cable limb and pilot limb are our cable current limit and pilot current limit when we're charging. Likewise, plug detect and pilot type. These relate primarily to our CCS fast charging. CCS available current, available voltage, our current CCS current, our current CCS requested current, our current CCS voltage, our station available voltage minimum, and our CCS voltage as measured at the contactor. So quite a bit of diagnostic stuff in here. HV charge is a flag that just goes on or off to tell us that we are in charge mode or not. Currently off. CCS condition is again diagnostic. This is transmitted from the CCS fast charging station to tell us what the station is currently doing. CCS state is just a measure of what component of the CCS state machine that we're currently in, so it's diagnostic. Charge port door and CCS contactor state. And down here then we have the current, day, hour, minute and seconds, our charging time. Finally, whether we have a heat request for cabin heating or not from the vehicle's climate control system. And finally, CPU load. So despite my crappy software, I cannot even get the STM32 to wake up. It's just yawn, really, Damien. Plot enables us to pick any of these values on the left or the right axes and plot graphs of them. Quite useful. And there is another feature here. I don't know if it's on this web interface. It's possibly not on this one. There's a data logger, which will let us actually log data into a CSV, I believe, so that we can log in data during driving and so forth to peruse later with our friends. So folks, that is a short walkthrough of our web interface. Okay folks, so I decided to cut the video there because it has certainly got a little bit longer than I had even intended this part of it to be. I did have some more footage shot where I was explaining the software updating and showing how it can go wrong. I'll include that in the next episode, and that should be along fairly soon, and we'll be working on our Nissan Leaf drivetrain out there and showing how to get that working and what can go wrong and what'll stop it from working, and just general, I guess, kind of a little bit more of the whole user manual thing. So in any event, I hope that you've enjoyed this video, but I can't really see how you could have, but okay. So as usual, don't forget to dislike, do not share, unsubscribe from this stupid channel, and for Pete's sake, don't support me on Patreon or PayPal or any of those things, because then I just keep doing this stuff. And let's face it, nobody wants that to happen. So, other than that, there will be some links in the description there for whatever other useful things that I can find. And I'll put the specific links in there for the VCU wiki page, ISA shunt, EV Create web shop for the shunt purchasing, and anything else that I can think of, I'll just throw in the description there for you. So that's it, folks, and until next time, happy VCU programming.